Hello students, this is the recording for the 2J lesson, Electronegativity in Groups. Today is day 22 out of 60. We are going to have a recording for today. Remember that there are no live sessions. The recording for today should help you complete the 2J notes. Don't forget that we do have live class tomorrow. Tomorrow will be a work day where we are working on the last few slides of our Unit 2 element project, and that will be due tomorrow after classes. So please make sure that you are attending class tomorrow. That way you are able to complete your Unit 2 project. Again, this is going to be our last content lesson of the unit, Electronegativity in Groups, and then tomorrow we will be finishing up our projects. The last few slides of our projects go over electronegativity, so that's why we needed to go over these lessons, and then we should be able to finish up our projects. Our objectives for today, we should be able to define a group in the periodic table. This is actually review. We should already know what a group is in the periodic table. We should also be able to explain how electronegativity changes based on atomic size. We actually just talked about this when we talked about electronegativity in periods. Today, though, we will be applying that also to then two groups. So which atoms in a group are likely more electronegative, again based on their atomic size. We will be completing the 2J notes, and you should be getting an 80% or higher on those notes, assuming you're following along, making sure that you're practicing before you do the application problems. So at this point, please go ahead and go to your Grades tab and open up your 2J notes. Links are in your Grades tab, just like always. Once you click on the link to your notes, you can go ahead and click Start Quiz. All right, so taking a look here, a row, this is all review. Remember that a row in the periodic table is called a period. That is in fact where the word periodic table comes from. And remember that elements in the same period have the same exact number of shells. So if we take a look at an example here, period 2, this row right here, they all have 2 shells, right? So you can see period 2, the number is 2, and they all have 2 shells. So you can see 1 shell, 2 shells. Remember, those shells are the rings of electrons around each element. Same thing with period 3. You can see that period 3, they all have 3 shells. 1, 2, 3, 1, 2, 3, 1, 2, 3, so on and so forth. Just a quick reminder that the smallest shell, such as in period 1 only has the first shell. You can see a shell here and a shell here. That small shell can actually only fit 2 electrons, and then it's considered full. That is why helium is considered noble gas, because its shell is actually full with 2 electrons. Even though that doesn't necessarily fulfill our octet rule, that octet rule is related to larger shells that can actually fit 8 electrons, like in period 2 and period 3. Now let's go ahead and talk about what we'll be focusing on today, which is groups. So remember that a column, which is the vertical up-down part of the periodic table, is called a group, or it can also be called a family. So if you take a look here, here is, for example, group 1, right? And you can see it's called group 1. It's also called the alkaline earth family, or sorry, the alkali metals family. So again, they can also be called families. Now, elements within the same group don't have the same number of shells, like in a period. Instead, they have the same number of valence electrons, so the same number of electrons on their outermost shell. So you can see here, for example, hydrogen has 1 valence electron, lithium has 1 valence electron, and sodium has 1 valence electron. Same thing if we jump over to group 17. You can see that fluorine has 1, 2, 3, 4, 5, 6, 7, and chlorine 1, 2, 3, 4, 5, 6, 7 electrons on their outermost shell, which we should know because the group number 17 ends with the digit 7, which is how we identify that it has 7 valence electrons. Okay, so again, in a row, horizontal, left to right, it's the same number of shells. In a group, up and down, it's the same number of valence electrons, which is just the electrons on the outermost shell. Now remember that the fact that they have the same number of valence electrons is related to how they bond, right? It's related to bonding, how many electrons they want to lose or gain, which is how atoms bond, right? So the result is they end up with very, very similar properties. So for example, group 1, which contains the alkali metals, our family, right, is going to have a lot of similar properties, such as lithium and sodium react very quickly with water in order to produce smoke, or if you get down to other elements, it can actually even produce explosions. So again, they're going to have similar properties. So based on this, you should be able to do this next application problem. So this one is a complete on your own. If you need any help on it, just rewind to the previous slide. Again, everything you need to know is on the previous slide. So we're talking about which of these things is related to groups, which of these things is related to periods. So you need to identify which one is the row, which one's the column, in which of these do elements have the same number of valence electrons, in which of these do they have the same number of shells, what is the result, in which of these do they have similar properties, and in which of these is also called a family. Go ahead and complete number 1, pause the video, and then continue playing when you are ready. Okay, so let's go ahead and review the term electronegativity. Remember, electronegativity has that root word electro, right? So we can actually know that it's related to electrons. Specifically, it's an atom's ability to attract electrons. Now, remember that this is kind of a weird thing to think about, but the smaller atoms are, they're actually more electronegative. All right, so this should be the way that you can kind of think about this is smaller atoms are cuter, like puppies are cuter than their adult versions. Right? Which, I mean, adult dogs are pretty cute too, but the smaller they are, the cuter they are, right? So smaller atoms are more electronegative, which means that they're more attractive to electrons. A good way to think about it is smaller atoms can actually grab new electrons more easily. They have less kind of empty space to try to, or they have less space where they have to try to move through to try to attract new electrons, that their nucleus has to try to attract new electrons. So based on this, which of these atoms do you think will be the most electronegative, and which do you think will be the least electronegative? Again, it's based on size, right? So the smaller you are, the more electronegative you are, right? Whereas the larger you are, the less electronegative you are, right? So smaller results in more electronegativity, and larger results in less electronegativity, or sorry, smaller results in more electronegativity. The larger you are, the less electronegative you are. And again, this has to do with how easy it is for you to reach a new electron. So taking a look here, the nucleus of lithium, which all nuclei are positively charged, is trying to attract a negative electron. So they just have to move through these two shells to try to attract a new electron, right, which I'll mark as a negative sign. Whereas in francium, its nucleus, its positive nucleus, has to reach through, let's see here, 1, 2, 3, 4, 7 different shells and a lot of electrons to try to reach a new electron. So that's why it's a lot harder for francium to attract new electrons. It is just too big. All right, so that should help you answer question number 2. Go ahead and pause the video and complete number 2, and then move on when you are ready. All right, so at this point, you should be able to answer this question. Which of the following statements is true about electronegativity? Again, you need to identify which types of atoms are more electronegative, larger or smaller atoms, or is atomic size not related? And then explain why, right? So is it because it's easier for them to reach electrons or harder to reach electrons? Again, the answer is on the previous slide, so if you do need help, go ahead and rewind to the previous slide. Go ahead, take a moment, pause the video, and continue playing when you're ready. All right, so taking a look here, as we go from top to bottom within a same group, remember that we are adding shells. So remember we talked about how each period tells you, right, how many shells they have, right? So this is period 1, this is period 2, period 3, period 4, period 5, period 6, and period 7. Right, and we saw that in period 1, right, there's 1 shell. Right, in period 2 we have 2 shells. Period 3, 3 shells, and so on and so forth. And you can actually see that right here in the pictures. So for example, you can see lithium, which is in period 2, has 2 shells, right? 1 shell, 2 shells. Period 3, which has sodium, has 3 shells, 1, 2, and 3. 3 shells or rings. Potassium is in period 4. It has 1, 2, 3, 4 shells. And rubidium is in period 5, and so it has 1, 2, 3, 4, 5. So within a group, right, so this is our group number 1, as you go from top to bottom, right, as we go from top to bottom, we can see that we're adding shells, right? So as we go from top to bottom, we are adding shells, okay? And the result is that we end up getting bigger and bigger, okay? So based on what we just talked about, we just learned that the smaller you are, the more electronegative you are, because remember, you can more easily reach electrons, right? So lithium right here is going to be much more electronegative than rubidium, right? Rubidium's just too large. This one's larger. It is less electronegative because it is harder to reach electrons, okay? So based on talking about that, we should know that as we go from top to bottom, right, it should make sense that if we have really high electronegativity up here and really low electronegativity down here, then that means that as we go from top to bottom, our electronegativity is decreasing, right? We're getting larger, and so it's getting harder to attract electrons. So again, moving from top to bottom, electronegativity decreases. And again, this is kind of wild to think about, but again, the smaller you are, the actual more electronegative you are. So at the top of our groups, we're actually more electronegative. At the bottom, we're less electronegative. And again, the reason why is because the more shells you have, the bigger you get. It just gets harder to attract electrons. And this has to do with something that's called shielding. So you can see that we have a bunch of shells in here, and all of those shells are hard for a nucleus to get through to try to attract a new electron. So our nucleus, again, is made up of a bunch of positive protons that are trying to fight through these shells to attract a negative electron. And so all of these inner shells just cause what is called shielding. It just makes it really difficult for the protons in the nucleus to attract an electron. All right, so this is going to be the answer to number 4. Go ahead and pause the video and continue playing when you're ready. All right, so which of these elements is likely the most electronegative? Again, the less shells you have, the smaller you are, and therefore the more electronegative you are. So again, we talked about this pattern that as we go from top to bottom, electronegativity decreases. So what this means is that you have the highest electronegativity at the top with your smallest atom, and you have the lowest electronegativity at the bottom with the largest atom. All right, so let's go ahead and take a look here. So again, carbon, right, if we were to label our periods here, this is period 1, period 2, period 3, period 4, period 5, and period 6. And again, this is also related to the number of shells, right? So this is the same as the number of shells. Okay, so if we take a look here, carbon right here is in period 2, which means that it only has 2 shells. Whereas if we take a look here at, let me grab this. If we take a look here at lead all the way at the bottom, lead is in period 6, and so that means that it has 6 shells. So in terms of size, we want to find the smallest one, and the smallest one is definitely going to be carbon. So carbon at the top is our smallest one, and that one is therefore the most electronegative, right? It is the smallest. All right, go ahead, pause the video. That's our answer for number 5. Make sure that that makes sense because the next one you need to complete on your own. Okay, so this one you should be able to then complete on your own based on that pattern. So again, think about the fact that you're trying to find the smallest atom. Remember, the way that you can figure that out is by looking at periods, period 1, period 2, period 3, period 4, period 5, and period 6, which is related to the number of shells, right? The period is related to the number of shells. Okay, so you should be able to identify which of these is the smallest based on its period and number of shells, and that one should be the most electronegative, right? So smaller atoms are more electronegative. All right, please go ahead and work on question number 6. Pause the video and continue playing when you're ready. Okay, so again, smaller atoms, we've said it 1,000 times, are more electronegative, more attractive. Again, think about the fact that they are what we could say as like cuter. right? So they're cuter. Now, we did talk about the pattern yesterday in periods, right? So we said in periods, atoms have the same number of shells, right? And so as you go from left to right within a period, you actually get smaller, right? So we can see here that, for example, if I were to take a look at here, right, you can see that as we go left to right, we actually get smaller on the right side, which means it's more electronegative. Smaller on the right, which means more electronegative, okay? But again, we talked about the reason why yesterday, and the reason why has to do with the fact that they all have the same number of valence shells, but they have different protons. So again, in this period, all of these are in period 2, and so they all have 2 shells. So they all have the same number of shells, but as you go from left to right, you can see that they're increasing their number of protons. Lithium has 3 protons, beryllium has 4, boron has 5, 6, 7, 8, fluorine has 9. So those 9 protons in fluorine, for example, are going to pull in or attract those 2 valence shells, those 2 shells, a lot more easily. So they're going to attract or pull in those shells, and that's going to make it smaller, right? Because they all have the same number of shells, they all have the same setup. So if you have more protons in the center, you can pull in your shells more easily. So here's a picture of what we went over yesterday, right? We compared carbon and nitrogen. Again, same exact setup. They both have 1, 2 shells, 1, 2 shells, but nitrogen has an extra proton. Its atomic number is 7. So it has 7 protons, whereas carbon only has 6. So this extra proton can actually pull in these shells more easily, and so it becomes smaller. And we know that if you're smaller, you're more electronegative, and again, this is going to be as we go to the right of our periodic table. Okay? So then let's go ahead and take a look. Oh, there is that exception, right? We ignore this last group, column, family. And the reason we ignore that is because those are the noble gases. Remember, they're in group 18, so they actually already have all 8 of their valence electrons. They have all 8 valence electrons, right? So they have full octets. And so they actually don't want to attract or get rid of electrons, and so they just, they have no electronegativity, because they don't care about electrons. Now, what we learned today, though, is that in groups, right, atoms have different numbers of shells, right? So as you go down in a group, you get more and more shells, right? So we can see more shells at the bottom. And as you have more shells, you actually get less electronegative because you're larger, right? So at the top of a group, that's where you're actually most electronegative, right? So when you have less shells, you are most electronegative. Okay, so again, we're more electronegative to the right and we're more electronegative to the top. So if we kind of overlap these, right, and we say, right, we're smaller on the right and we're smaller on the top, smaller on the top, and therefore more electronegative, then that should make sense for why fluorine is the most electronegative atom on the periodic table, right? Because our electronegativity is increasing as we go to the right and get smaller, and our electronegativity is increasing as we go up and get smaller with less shells. Okay, so that's where we get this overall trend here, is that francium is one of the larger, right? So this is a larger element on the periodic table. And so on the periodic table. And so this one is way less electronegative, so much so that it actually prefers to give away electrons than take them. Whereas smaller element, fluorine at the top here on the periodic table, is more electronegative. Okay, so again, we get smaller as we go up and to the right, and we also get more electronegative as we go up and to the right. So that's our overall trend here. So that should help us figure out what's going on in this next slide. All right, so which of these elements is likely the most electronegative? Again, it's going to get higher as we go to the right within a period or row, and it's also going to get higher at the top of our groups where we have less shells, right? So higher to the right, you're smaller because you have more protons to pull in the same shells. Right here, I'll just put that up here. Okay, and it's also higher at the top of groups because you are smaller with less shells. Okay, so again, the smaller we are, the more electronegative. That's going to that electronegativity is going to increase as we go to the right, as we go to the top, because we get smaller as we go to the right or go to the top. So taking a look here, we want to know which of these elements is the most electronegative. The easiest way to do this is to highlight everything that's on the right of a period and everything that's on top of a group. So taking a look here, I'm only taking a look at these 9 elements right here. Let me go ahead and grab a different color here. Perfect. All right, so if I highlight everything on the right of a period, all right, that's going to be these 3 elements, sulfur, selenium, tellurium. And if I highlight everything at the top of a group, that's going to be all these 3, silicon, phosphorus, and sulfur. And the only place where they overlap, the one that's going to be the most to the right and the most to the top, is going to be our sulfur. So the correct answer here should be sulfur. Sorry, let me grab a different color. Here we go, sulfur. Okay, again, because it's both the one most to the right as well as the one most to the top. So of these 9, it's going to be the smallest. Most to the right, it has more protons to pull in its shell. And of those shells, it has the least amount of shells. So it's pulling in the least amount of shells, and so that is going to make it the smallest. So that's our answer to number 7. Make sure that that makes sense, and then go ahead and move on to question number 8, which you will try to do this on your own. All right, so question number 8 says which of these elements is likely the most electronegative? Remember, we have this pattern, right, that we get smaller and more electronegative as we add protons to the right in a period, and we get smaller and more electronegative as we have less shells at the top of a group. So again, I would recommend go ahead and just figure out which of these are all to the right, which of these are all to the top, and where do they overlap? Because where they overlap, that'll be the element that is both furthest to the right and furthest to the top. Go ahead and complete number 8, and then continue on when you are ready. Okay, so at this point we should be able to kind of take a look at our definitions of electronegativity overall. So we want to know where do we have higher electronegativity and better ability to attract electrons, and where do we have lower electronegativity, less ability to attract electrons. So your options are, taking a look here, the left side of a period where elements have less protons to pull in their shells, the right side of a period where elements have more protons to pull in their shells, the bottom of a group where elements have more shells, or the top of a group where elements have less shells. Again, think about their sizes. All right, so in comparing, right, the periods, think about which one's going to be smaller. Remember, smaller is more electronegative. Okay, and same thing here. Think about in the groups, which ones will be smaller, because smaller is more electronegative. Remember, lower electronegativity is when we have larger atoms. Right, so smaller atoms versus larger atoms. All right, go ahead and pause the video. Continue playing when you are ready. If you need help on these, I would just recommend rewinding and going back through the lesson. All of the answers here are in the lesson. All right, so today we talked about groups on the periodic table. We talked about how electronegativity changes based on atomic size. Remember, the smaller you are, the more electronegative you are, and we specifically applied that to groups, right? Groups, we said at the top is more electronegative because they are smaller, and that is because they have less shells. And again, the smaller you are, the cuter you are, the more electronegative you are. It's easier for you to reach electrons. All right, so make sure that you have completed your 2J notes here. Make sure that you confirm the statement that you understand that you cannot pass this course unless you correctly do the projects and exam. And I will see you later. Thank you so much.